Dear students, we are going to start the second chapter of thermodynamics. We'll have a quick revision of the second chapter, which is heat and work. I'd like to start with a question. Which of the two do you think has more energy? 1 kg of air at temperature 100 degrees centigrade or 1 kg of air at velocity 100 meter per second? Suppose you have to design a rocket and you have to choose one source of energy. Which one would you choose? Heated air or air moving with very high velocity? You'll be able to answer this question within few minutes of this video lecture. So let us start with what are our learning objectives, what we are going to cover up today, right? It is going to be fast. We are going to cover up forms of energy. Energy is the soul of thermodynamics, right? So we have to cover up what are the different forms of energy, like internal energy. We'll cover up heat transfer, work transfer, part versus point function, displacement work for various processes. What is specific heat? What is enthalpy? What is quasi-static process? And zeroth law of thermodynamics. And finally, temperature measurement. So without wasting any time, let us start. Energy. Energy is the soul of thermodynamics, isn't it? Because we defined thermodynamics as study of energy, how energy can be converted into useful work, power. So whenever we are studying thermodynamics, the most important thing that we should do at the initial stage is to study energy. Now, energy can be broadly classified into two types, macroscopic and microscopic. Macro is something which you can see with our eyes. Micro is something which we cannot see with our eyes. The macroscopic energy are the energy, for example, kinetic energy and potential energy. We keep on dealing with them in engineering mechanics, right? This is something very common and we can actually feel, like, and we also know, right? Most of us know that kinetic energy can be written as half m v square, sorry, half m v square, right? And potential energy in thermodynamics will be represented as mgz, where z is the elevation from ground. And these are the energies that we can see, right? And but the microscopic energy, which is more important in case of thermodynamics, is something which cannot see, which is molecular level energy. It is divided into four parts: sensible energy, latent energy, chemical, and nuclear. So let us try to understand what are these forms of energy. The sensible energy is the energy because of the vibrations of the molecules. Now the molecules will have vibration, translation, spin, rotation, all different types of vibrations it is going to have. Now the energy possessed by the molecules because of these vibrations is known as sensible energy. Now let me tell you, the sensible energy is the most important of all these energies, and it is directly proportional to temperature. As we increase the temperature, vibration increases. As a result, sensible energy increases. So in thermodynamics, try to understand this very nicely. In thermodynamics, whenever we are increasing the temperature, the energy that increases is the sensible energy. Thereafter, the second most important energy in thermodynamics is the latent energy. This is the energy which is related to phase change. Whenever solid changes into liquid or liquid changes into vapor, the energy that is required, we call it latent heat of vaporization, latent heat of fusion, right? And we are going to use this. Then comes the chemical energy. Chemical energy is the energy that is stored in the bonds. Chemical bonds, be it covalent bonds, be it ionic bonds, there is immense amount of energy stored in these bonds. And this energy generally gets released whenever we burn the fuel. For example, we have fuel, combustion of the fuel takes place. The energy that is released, the heat energy that is released in combustion, it is because of the bonds, the chemical energy of the bonds gets released. Right? And finally, nuclear energy. It is the energy, immense amount of energy which is stored in a nucleus. We get to see it in nuclear fission or nuclear fusion reaction. Right? Now, let me tell you, in thermodynamics, you hear the term internal energy. We represent it by U. We're going to see it in some time. The microscopic energy is the energy, right? Microscopic energy is the energy which is the internal energy of the thermodynamic system. Having said that, let us try to define what is microscopic energy. Microscopic energy is the energy processed by the system as a whole, and it is always relative to a frame of reference. So whenever we are seeing potential energy, we see it with respect to ground. If you change the frame of reference, the energy, the potential energy will change, right? Similarly, velocity is also something with respect to frame of reference, right? So the velocity will also change if the frame of reference changes. So it is very important whenever we are looking at the macroscopic energy that we choose the proper frame of reference, like ground, right? Earth. Okay. On the other hand, microscopic energy is independent of any frame, outside frame. From whichever frame you look at it, it will always have the same amount of energy, and it is basically because of the molecular structure and the molecular activity. The microscopic energy you have seen, they are sensible, right? This is because of the vibration, right? Latent, phase change, chemical, atomic bonds, and nuclear, that is associated with the bonds within the nucleus of a atom. Now, always remember that temperature is directly proportional to sensible energy. Whenever you are increasing the temperature, the energy that increases is the sensible energy, that is the vibration of the molecules. Having said that, I can say now that internal energy, we have learned that internal energy is a sum of sensible, latent, chemical, and nuclear. And if you want to find out the total energy, right, the total energy is basically the internal energy, which is the above, plus the kinetic energy and potential energy, which is the macroscopic part of the system. Now, if you take a special case, if the system is stationary and the elevation is constant, so what we can say, right? System is stationary means velocity is zero. Elevation constant means there is no change in potential energy, right? In that case, we can say total energy of the system is equal to internal energy. And I'd like to make a point here. We are never interested in the total energy or the total internal energy. What we are interested is change in total energy or change in internal energy. Because you have learned that energy can neither be created nor be destroyed, right? It can be converted from one form to another. So the energy, the internal energy, if it changes into work, so how much energy has changed? That is what we are interested in. We don't want to know what is the total energy, absolute total energy or absolute internal energy of a system. Only the change part is what we are interested, right? And we will understand this as we go ahead. We are going to understand this. Now let us try to answer this question: which has more energy, right? Is it 1 kg of air at temperature 100 degrees centigrade or 1 kg of air at velocity 100 meter per second? So you can understand that this one is related to kinetic energy, right? So what is the total energy? Half m v square. So mass is 1 kg, so this is half into 1 into velocity is 100 square. So this is coming out to be something around 5000 joules. Joules is the unit of energy, so this is 5 kilojoule. Right. So let us now try to see what is the energy associated with 1 kg of air at temperature 100 degrees centigrade. Now let me say initially the air was at 0 degree centigrade, right? So from 0 degree the temperature was raised to 100 degrees centigrade. So how much energy, increase in energy was there? How much energy was supplied? So we say this is heat energy, heat transfer is equal to, okay, it will not have, it will rate, it is just the heat transfer. Now why we call it heat transfer, we will understand it in some while, right? So heat transfer is given as mc delta t, right? M is the mass, c is the specific heat capacity or heat capacity. We'll understand it slowly, right? We're going to understand in today's class itself what is the c and what is this definition, how to use it, and this is the change in temperature, right? So mass is 1. For air at constant pressure, okay, if I'm talking about constant pressure, or let me take constant volume, okay, I can take constant volume, I can take constant pressure, right? I'm taking the least one. Okay, let me take constant volume, right? Constant volume is less. Now, why it is less, why it is more, right? We are going to talk about it, right? It is 0.718 into delta T is coming out to be 100. So this is coming out to be 71.8 kilojoule. This unit is in kilojoule per kg Kelvin. So you see, I'm just giving you an overview. See that the energy possessed by air at 100 degrees centigrade is almost 15 times the energy of air at 100 meter per second. The same quantity of air. And that is why the heat energy is so very powerful, right? The energy possessed by the system because of temperature, the sensible energy is so very powerful. It is much higher than something which is moving with the kinetic energy part, right? So if we are able to convert heat into kinetic energy as we do in our rocket propulsion or in our jet engines, right? It can give us immense amount of thrust. And that is why the subject of thermodynamics is very important. Having understood this, let us move forward to understand energy transfer mechanism. Now we have seen that energy, right, basically it is the total energy which is macroscopic plus microscopic, or it is the internal energy which is basically the microscopic part, right? Now this is the energy stored in a system, right? But in thermodynamics, we'll have to figure out how this energy is being transferred from one system to other or from the system to surrounding. There are two methods by which the energy can be transferred, and they are heat transfer and work transfer. So let us understand what is heat transfer and work transfer. First, let us start with heat transfer. Now, heat transfer is the transfer of energy, right, between two systems. Sorry, is a transfer of energy between two systems by the virtue of temperature difference, be it two systems or systems of surrounding, right? If the energy is getting transferred because of difference of temperature between the system and surrounding, we call it heat transfer. Now, many students do confuse that heat is a form of energy. No, it is not a form of energy. It is energy in transition, right? Earlier, before Joule did his Joule experiment and gave us the first law of thermodynamics, people used to think that heat is a form of an energy. It is stored in a body. No, it is not so. Heat is in energy. You have already seen energy is microscopic or macroscopic, right? We can microscopic. You can call it as internal energy, and sensible energy is the energy associated with temperature. But this is not heat. What is heat? Heat is when the energy is getting transferred from one system to another because of temperature difference. Let us try to understand this clause because of temperature difference. Now, I have a room which is at 25 degrees centigrade, and in this room on a table are kept 3 cups of coffee. The first cup of coffee is at 25 degrees centigrade. The second cup of coffee is at 5 degrees centigrade, and the third cup of coffee is at 80 degrees centigrade. Now let us try to understand what is heat transfer. Now if you take the first cup of coffee, the temperature of the coffee and temperature of the room is same. So what will happen? There is no heat transfer taking place. Total heat transfer is going to be zero. Heat transfer, we represent it as Q. Total heat transfer equal to zero. Neither from coffee any heat will go to the room, nor from the room heat will come to the coffee. Let us take the second case where temperature is 5 degrees centigrade. So you see the temperature is less than that of room. So what will happen? Heat will flow into the coffee. From the room, heat will flow into the coffee, and slowly what will happen? The temperature 5 degree will rise, and slowly it will go to what? It will reach 25 degrees centigrade. Right? Eventually, it will take some time, but eventually it will go and reach the room temperature. So you can see because of temperature difference between the surrounding and the system, there is a temperature difference. It has flown into the system. Right? Now let us take the third case, 80 degrees centigrade. You can see the coffee is at a higher temperature, right? Room as it is at a lower temperature. There is a temperature difference, right? And because of this temperature difference, what happens? The heat flows from the coffee to the room. right? And slowly after some time, the heat will keep on flowing till the temperature difference is there, right? Till the temperature of the coffee is more than that of the surrounding the room. Heat will keep on flowing from coffee to room. And finally, when both of them becomes equal, that is when the heat transfer will stop. So you understood that heat transfer is transfer of energy between between system and surrounding, or between two systems, because of temperature difference. That clause temperature difference is very, very important. Why it is important? We'll understand it in short one. Now let us see what will happen if there is no heat transfer across the system boundary. Now, heat and work are boundary phenomena, right? We only when there is a energy transfer because of temperature difference between system and boundary, we call it heat transfer. Now see this. Now this is an insulated container, right? This container is insulated container. The candle is burning inside. Assuming that there is enough oxygen, you can see a lot of heat is being created. The chemical energy of the candles are being converted into heat energy. So temperature of the system will definitely increase. But is there any heat transfer? No, the heat transfer is zero. Why? Because the system is insulated. So a process is taking place. The state of the system inside, right, is changing. It is a certain temperature, the temperature has changed, right? But there has been no heat transfer. And such process where there is no heat transfer, we call them those processes as adiabatic process. Now, a process has taken place, isn't it? Because the candle is burning, right? The state of the system will definitely change. From initially it will be at some temp state, right? And then finally it will be at some other state. The state will change. So a process has taken place. But in this process, there has been no heat transfer, right? Because I have insulated this room. And such processes are known as adiabatic process. Energy transfer by work. Okay, now this is interesting. I told you that heat transfer is because of temperature difference, right? So any other transfer of energy, right? Any other transfer of energy which is other than heat is work. What do I mean by other than heat? Means any interaction of energy which is not caused by temperature difference. If any interaction of energy, if any transfer of energy takes place, which is not because of temperature difference, will be considered as work. If it is because of temperature difference, it will be considered as heat. So let us see what are the different types of works. Displacement work, right? For example, the piston moves because of the expansion of the gas, right? This is displacement work. Displacement work is the work we use in our IC engines, right? Internal combustion engines, which are in our automobiles. Shaft work, right? When the shaft rotates, this is also a work done. Now, this kind of work done is available in pumps, compressors, turbines, right? Turbines, what do they produce? They produce shaft work, right? We are going to deal it with electrical work. Now, if there is a resistor, right, and current is flowing, and because of which the heat energy, the energy which is there in the electrons are converted into what? Heat energy. Basically, it is not the right thing to say heat energy, right? If we really want to describe it with respect to thermodynamics, right? This is work transfer. Though the room is getting heated up, the temperature of the room is increasing, but this is basically not because of temperature difference between the room and the surrounding. Try to understand this. Suppose we are heating a room, we have kept the heater inside the room. The heater coil is, say, red, it is hot and it is releasing energy. Now this will not be considered as heat transfer. Why? Because this is not because of temperature difference between system and surrounding, right? It is not because of temperature difference between system and surrounding, because the heater is already placed inside the room, right? And the surrounding temperature will be lower. In fact, it is getting transferred from the room to the surrounding, right? We use heaters in winters, isn't it, to keep our room warm. So the room is at 25 degrees centigrade, outside temperature is 5 degrees centigrade. So where is the heat transfer basically happening? From room to the surrounding, right? Not from the heater to the room. Okay. Flow work. Work associated with flow, we are going to learn about this flow in some time. Paddle wheel work, right? Uh, Stirrer, right? We are using a stirrer, right, to stir the uh, fluid, right, liquid mostly, right? We call it paddle wheel work, and we are going to see most important ones are displacement work and flow work. This is something we have to understand in detail, especially displacement work. Calculating shaft work is not a very difficult term. We will see when we are studying compressors, turbines. We'll see what is exactly shaft work. Having said that, let us try to understand what is a sign convention. Now, to solve any question on heat transfer, which is where work and heat are involved, we'll have to use the sign convention. This is very, very important. Now, the sign conventions are as follows, right? If the system is doing the work, if system is doing work, we call it positive. If heat is going into the system, we call it positive, right? If the heat is going out, we call it negative. If work is done on the system, again, we call it negative. Okay. Now, when I was a student, I used to get confused with which one is positive, which one is negative. Now, basically, there are three ways this can be remembered. The first way, you are a you have a very strong memory, right? You whatever you read once, you never forget. Unfortunately, I'm not that kind of person. So, the second method is that you practice enough questions. You practice so many questions that these things gets ingrained to your brain permanently, right? Solidify in your brain. Right? And unfortunately, when you're preparing for a competitive exam, practicing so many questions from one sector, it becomes sometimes difficult. Once you know the concept, once you have solved few number of questions and you see that, okay, I'm able to solve it, right? Then you generally move on to the more complex things, right? So what happens if you have understood it well and if you have not practiced questions for a long time, say, then there is a probability that initially you forget, right? So the third way is to remember using mnemonics, which I use. So that is why I can remember it even now, right? I'll just tell you, give you a hint how to remember this, right? It might be useful for you. For example, suppose heat is going out. Now I consider the system as my bank account, right? I consider the system as my bank account. So heat is kind of money, right? So whenever money is coming in, this is positive because, right, money coming in. Money coming into my bank account, right? Obviously, my bank balance will increase, so this is positive. If money is going out, right, it is negative because my bank balance will decrease. It becomes very easy for me to understand. Now, work. Now, if I am doing the work, obviously I will get paid. And if I get paid, again, my bank balance increases. So that is a positive. But if someone is working for me, right? I'm doing the work, system is doing the work, work is done on the system. Means someone is working on me or working for me, right? Obviously, I'll have to pay him. So what happens? My bank balance decreases, so negative. So this is a simple mnemonic which I use, right, to remember this. You can do the same, or you can actually invent one of your own. Having said that, I'd like to start with another question. Now, suppose I have 1 gram of water and 1 gram of iron, and I transfer 100 joule of energy to both water and 100 joule of energy to iron. What will be the increase in temperature of water and iron? Will there be any increase in temperature, first of all? If yes, what will be the difference? Will water's temperature increase more or iron's temperature increase more? And what will be that increase in temperature? How to calculate it? Now, to understand this, to help us with this calculation, specific heat comes to our rescue. So, what is specific heat? It is a property that describes the substance capability to store energy. How much energy the substance or whatever our system can store. and it can be defined as energy required to raise the temperature of a unit mass of substance, right? Unit mass like 1 gram, 1 kg by 1 degree centigrade. So its unit is joule per gram per centigrade or joule per kg per centigrade. How much joule of energy is required to raise the temperature of 1 gram of substance by 1 degree centigrade? Now let us take the example. 100 joule of energy to water and 100 joule of energy to iron. Now the specific heat capacity of water is approximately 4.184 joule per gram per degree centigrade. Means it takes this much of energy to increase the temperature of 1 gram of water by 1 degree centigrade. So if you're supplying 100 joules, so we'll simply divide 100 divided by 4.184. So the temperature increase of water is going to be 100 divided by 4.184. It is coming out to be 23.9 degrees centigrade. 23.9 degrees centigrade. Right? Similarly, if we talk about iron, right? If we talk about iron, right? What the specific heat of iron is 0.45 joule per gram per degree centigrade. What it means that if we supply 100 joule of energy, right? And this is a specific heat, sorry, 450, right? So it is going to be how much? 100 divided by 0.450, it is coming out of 222. Oh my God. Right? So the same temperature, same amount of heat you are supplying, but you see the increase in temperature of iron is much, 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 much higher. So basically, I can comment that water has the more capability to store, right? Heat. And yes, it is liquid. Liquid do have more capabilities, right? Than solid. Okay, and that is why also water specific heat is so high. That is also why we use it in our vapor compression cycles, because it is very useful. It can store a lot of energy and transport a lot of energy, right? Now, where did this formula come from? Let us try to understand. This formula is basically, right, this can be said to be something like this. Total heat transfer is equal to mc delta T. This is the C we are talking about, right? For water, it is 4.184 and for iron, it is 0.450, right? So this is the amount of heat transferred is equal to mass multiplied by specific heat multiplied by delta T, right? So it is given that heat transferred is 0, mass is 1, right? Specific heat, we'll have to use it here, and this is delta T, right? So what you can say, delta T is basically nothing else but 100 divided by the specific heat, and this is the exact formula that we've used here and here, right? Now, the funny case is that for solid and liquids, there is only one specific heat, right? There is only one value of C, but for gases, there are two. We have specific heat at constant volume and specific heat at constant pressure. That's why I wrote CV out there when we were dealing with air, right? I said specific heat at constant volume. CV for air is 0.718. CP for air is 0.1.005, right? Kilojoule per kg Kelvin. Now, why there are two? Because the primary reason being gases expand when we heat them. Unlike solids and liquid, right? Which does not have much considerable change in volume. If we heat them, gases can have massive expansion, right? Massive change in volume, right? When they are being heated. And that is the reason we have two different specific heats. Let us try to understand this, right? Why there are two? Let us try to understand this. And what is the difference between the two? The specific heat at constant volume. Suppose we have a container whose volume is constant. It has a substance which mass is 1 kg. I want to increase the temperature by 1 degree centigrade, right? And given that the CV, constant specific heat at constant volume, is 3.12 kilojoule per kg. Okay. So what it means, right? when I'm heating the system, when I'm supplying some heat, into the system, right? Now volume cannot change. Volume of the system cannot change. It is constant fixed boundary, right? So there is no work done by the system. If the volume cannot change, definitely the system cannot do any work. And all the energy, all the heat energy that is being supplied to the system results in increasing the internal energy of the system, right? So basically, if the CV is equal to 3.12 kilojoule, what it means that I need to supply 3.12 kilojoule of energy to the system, right? If we want to increase its temperature by 1 degree centigrade. Now let us first discuss what is specific heat at constant pressure, then we'll compare both of them to have a better understanding. Now you see the system, in the second system, we have a piston here. And the piston is movable. It can go up, it can come down, right? Now here we have same amount of mass, 1 kg, right? The temperature, again, we want to increase in temperature by 1 degree centigrade, right? And we are keeping the pressure constant here, right? Now, when we are supplying some heat, what is happening when you are supplying some heat, right? When we are supplying heat, definitely the temperature will increase to some extent. The internal energy, the sensible energy of this system increases. But at the same time, what is going to happen is that the piston will also move up, the gas will expand. And when the gas expands, we do some amount of work. When the piston expands, we do some amount of work. So what has happened is that the energy that has been supplied, now let us see what is energy that has been supplied, are resulting in two things. One is the increasing temperature, that is changing the sensible energy part. And at the same time, it is also pushing the piston. Some amount of work is also being done by the system. So as a result, to increase the temperature by 1 degree centigrade, more amount of heat will be required because temperature is increasing. But all the heat supplied is not going to increase in the temperature. Some amount of work is also going to what? To do the work, because the gas is performing work by moving the piston. And that is why more amount of heat is required, right, to raise the temperature by 1 degree centigrade. Mathematically, we can write CV as change in internal energy by dt at constant volume, and mathematically we can say Cp is equal to delta H. Delta H means enthalpy. What is H? We are going to learn about enthalpy in some time. H is enthalpy, right? dH by dt at constant pressure P. Mathematically, those terms we'll learn it later on whenever we are uh, trying to do something. Now you understood this concept. The value of Cp will always be greater than Cv. And why? Because in case of Cv, constant volume, the heat added is always going to increase the temperature. All the energy stays inside. But in case of Cp, right, constant pressure case, right, the heat added, it increases temperature, and also there is some amount of work done. The gas expands and some energy leaves as work. So to increase the temperature by same amount, we want delta T is same for both the cases. We want an increase in temperature of 1 degree centigrade, right? More amount of heat will be required for the constant pressure case than the constant volume case. If you have any doubt, any confusion, always you can type in the chat box. I'm there to reply for you. So let us summarize the energy transfer by heat and work. Both heat and work are boundary phenomenon, right? Whenever the energy crosses the boundary, we say the heat and work are defined only when the energy crosses a boundary. Anything which is happening within the system will be not considered as either heat or as a work. We saw that example in the burning candle case, right? The candle was burning inside an insulated room, right? There is no heat transfer taking place, though the temperature within the system is changing, and lot many things are happening within the system. The system possesses energy but not heat and work. We have to understand this energy is property of a body, but heat and work are not properties. They are not properties of the body, they are energy in transfer. Both heat and work are associated with a process. Whenever a process takes place, we say heat transfer or work transfer has taken place. It might be E0, but heat transfer and work transfer only takes place when there is a process, right? And unlike properties, heat and work does not have meaning at a particular stage. Suppose it system is at temperature T1 and volume V1, right? That for that temperature and volume do have meaning, right? The pressure, internal energy will have meaning, enthalpy will have meaning, but there is no meaning of heat and work when this is at a particular state. Only when the state changes from 1 to 2, we say the process has taken place, and that is when, right? A state will change from 1 to 2 and a process has taken place. That is when we say, that is when heat and work comes into picture, right? And both of them are path function. It is dependent on path, not on only on the points. Let us quickly understand what is path and point functions. So point functions are functions which are dependent only on the state of the system, initial and final state. Right? It is point functions are only dependent on initial and final states, and they are known as exact differentials. Right? The properties of the system, pressure, volume, temperature, right? We'll see what is that. Path functions are path dependent. They are dependent on the path that is taken in a process rather than just the starting and initial and the final states. And why we're talking about path and point functions? Because heat and work, right? Both of them are path functions. Let us have an understanding. Now, suppose the system was at state 1 initially. You can see the pressure was P1, right? The volume was V1 1 meter cube. It underwent a process, right? And it went to point 2, right? Where the pressure is P2, right? And the volume is 5 meter cube, right? Now, if you want to talk about volume, right? Delta V is V2 minus V1. Directly, you can write it this way. Or you can also say integration of volume from 1 to dV is equal to V2 minus V1. So change in volume you can directly calculate by subtracting the volume at point 2 minus volume at point 1, right? That is why it is a path function. And since you can write it this way, it is an exact differential, right? But can you write the work done in the process as work 2 minus work done? No. It is not just dependent on the initial and final stage. It depends on the process that you are taking, process that is going through. Is it a process B or is it a process A? Because different processes will have different work done. This is just tentative. I'm showing you the work done in process A is 10, then work done in process B is 15, though they are moving from same initial to final stage. And you cannot write work done as W2 minus W1, right? That is why they are known as inexact differential. You have to know the process. What kind of process is being followed? Is it a constant pressure process, constant volume process? Is it isothermal process, adiabatic process, adiabatic isentropic process? We'll discuss all this process slowly, okay, as we move forward. Right. So this is the basic meaning of uh, path, path function and point function. Now, if you talk about heat transfer, we have understood that heat transfer can be given by this equation, right? Let us summarize how to calculate heat transfer. So, heat transfer, it is represented by Q is equal to mc delta T, right? For solids, we have only one value of C, right? For solids and liquids, it is mc delta T, right? But for gases, it depends. Heat transfer depends. Either you will be using mCp delta T or you will be using mCv delta T. Delta T. This is not delta P. Okay. So this is for constant pressure process, constant pressure, and this is for constant volume process. So you can see heat transfer, right? Though the delta T might be same, right? It is dependent on which path you are taking. Are you taking a constant pressure process or are you following a constant volume process? And there are more others also. We'll see about them later on, right? And how to calculate the heat transfer for other processes we are also going to learn, right? in our future classes. Now, among work transfer, the most important work, right, which is the engineers are interested, is the displacement work, right? As I told you, the example of a very good example of a displacement work is the piston, the movement of the piston during the power stroke of engine, right? IC engine, right? The power stroke of IC engine that generates the work. So we are very much interested in displacement or bound. So we are very much interested in displacement work. Let us try to figure out how to calculate the displacement work. Now suppose I have a system, right, which is at a pressure P, right? There is a piston. The area of the cross-sectional area of the piston is A. Now, the pressure P applies the pressure and the piston moves forward by a displacement, a small displacement ds. There's a small displacement ds, right? So what can I say? What is the work done? Work done is the force multiplied by the displacement. Force into displacement. And force is nothing else but force is what? Force is pressure multiplied by the area. Because pressure we write it as force by area, right? So I can write force is equal to pressure into area. So I have replaced force as pressure into area to ds, right? Now what is area into ds? The area is the cross-sectional area of the piston multiplied by ds is nothing else but the change in the volume, that is dV, right? Change in volume, this much of volume, the change in volume, that is equal to dV. So this is the small amount of work done when the piston moves by small distance ds. Now what if there is a huge movement of the piston, right? Lot of displacement is there. So if you want to calculate the entire work done, it is simply integration of p dV from state 1 to state 2. Right, integration of PdV from state 1 to state 2. Let us try to understand it using a graph, right? So initially the system was at disposition at point 1. Initially the system was at point 1 and it undergoes a process and it goes to point 2, right? Initially this was the piston position of the piston, right? So displacement work happens and the piston goes to this point, right? So you can see the gas is expanding, the gas is doing some work, right? So how can we represent the work? So work will be basically work done in the entire process is equal to integration from point 1 to point 2 P dV. P is the y coordinate and V is the x coordinate. Now if you see this integration of P dV is nothing else but the area under the curve. Right? If we integrate it, what is it? It is nothing else but the area under the PV curve. So you can also calculate the work done by calculating the area, right? It's the same thing, right? Work done is nothing else but the area under the PV curve. Right? This is something that you need to understand, and this is how the process will look like. The system changes from point 1 to point 2, right? Now, the area on this is you will be able to understand that work is a path function by looking at this diagram, right? Because you see the area under the curve in process A, B, C will be different, isn't it? Now depends the system is coming from point 1 to point 2. The system is going from point 1 to point 2 by 3 different paths, A, B, and C. You can clearly see the area under the path of C will be lowest. So work done in case of C is the least. Work done in case of A is the highest, biggest. Why? Because the area under the curve is maximum. And this also tells us that work done is a path function and not a point function. Point function only depends on the instance, like the pressure. What will be the difference in pressure? You can simply say it is equal to P2 minus P1. What is delta V? You can simply say it is V2 minus V1. But what is work done, delta work done? Can you say it is W2 minus W1? No, I cannot say this. And that is why it is a path function and not a point function. Having said that, what will happen if there is a cyclic process? Suppose the system goes from point 1 to point 2 and then return back to point 1, as you can see here, right? It goes from point 1 to point 2 and then return back from point 1, right? So when it travels from 1 to 2, this is the energy, this is the work done, right? Area under the curve. When it travels from point 2 to 1, the area under the curve is this. So you can see there is a net amount of work done. You can see which is the work done which is covered inside the cycle. So the net work done during a cycle is the difference between the work done by the system and the work done on the system. This is work done by the system. This is positive, and this is work done on the system that is considered to be negative. And the net work done is the difference of two, that is the area under the cycle. Right? No worries, we are going to do a lot of problems and we are going to understand all these things in detail, right? So if you have any doubts, just keep on posting in the chat box so that I can help you figure out your doubts. Having said that, right, let us try to calculate the displacement work for the following processes. So we have constant pressure process, constant volume process, isothermal process, polytropic process. Now I want to, at this point of time, I know it is very early, so I just want to discuss the first 2 points initially, right? Isothermal process, polytropic process, I'll just simply introduce it, but we will have a much better look at it later on. Now let us look at the constant pressure process. So this is the constant pressure process, right? So in constant pressure, you can see the system is moving from point 1 to point 2 and the pressure is constant throughout the process, right? It is this pressure, right? So work done is equal to, can be written as, in the process 1 2 can be written as integration of P dV from V1 to V2, right? So pressure is constant. Let me say the pressure is P. Integration of dV will change from V2 minus V1, right? So this is very simple, and you can see this is nothing else but the area of the curve. This is the area of the rectangle between this area under the process curve, right? So it is very easy to calculate what is the work done in a constant pressure process. It is even easier if you want to calculate the work done in a constant volume process. Now you can look at the curve and tell me, right? What is the area under the curve? The area under the curve is simply 0. Right? There is no area. So definitely in a constant volume process, the work done will be 0. We can see it mathematically also. Work done in process 1 2 is equal to integration of V1 to V2 PdV, right? Here the pressure changes, but what happens to pressure is changing, no doubt. Pressure, you cannot write it as constant, you cannot take it out, but definitely what is volume? Volume V2 minus V1 is 0, and since V2 minus V1 is 0, right, there is no point calculating anything else. That anything multiplied by 0 is 0. So the total volume for total work done in a constant volume process is 0. Now let us try to have a generalized look at what if any other process can be is there. Now we'll talk it in detail. Now we are not in a stage where we'll be able to discuss all the processes, because the value of n, if it is 1, right, it is known as isothermal process. How? We'll talk about it. Okay, let me give you a brief idea. Now PV to the power n is equal to constant. This is known as polytropic process. Any process can be represented using this, using the value of n, right? We'll talk about this later on. When n is equal to 0, right, it becomes P is equal to constant. Okay, I'll change the color of the pen. When n becomes 0, it becomes what? N is 0, V to the power 0 is 0. Sorry, V to the power 0 is 1. So P into 1, that is pressure becomes constant, right? So this is the line which is representing n is equal to 0. Similarly, when n becomes infinity, it becomes volume is equal to constant. We are going to learn about this. Okay, don't worry, right? But not today. We'll take a separate lecture on this, and where we will understand this even clearly, right? Similarly, when n is equal to 1, this is known as isothermal process. PV is equal to nRT, right? And when n is equal to 1.4, it is known as adiabatic isentropic process. We will discuss it at that point of time when we have already discussed enthalpy, entropy, and finally we are drawing the PV curves, right? And before that, we'll also try to calculate the work done, and I'll take a separate lecture on that and where we are going to discuss. But yes, if all these processes can be summarized into one, right, that is polytropic process, right? Even if it is beyond any of these ends, right? So for a polytropic process, we can write down the work done. This becomes the formula for work done. Don't worry, we'll derive it again in our class. So I'm just giving you a hint at this point of time so that you have the picture in mind, but we are going to do it even further, right? Now, having said that, let us come to quasi-static or quasi-equilibrium process. It is very important to understand quasi-equilibrium process. Why? Because all the processes that are taking place, right, it should be in quasi-equilibrium state. Now, what is quasi-equilibrium process? As you can see, the processes which takes very, very slowly, all the processes which goes very, very slowly are known as quasi-equilibrium process. Now, let us take an example. Okay. Now, you see there is a gas which is contained by piston, right? There are two systems. You can see two diagrams. One, I have kept sand on it, and one I have kept a stone on it. Now, if you take out the stone, what do you think will happen? If you just take out the stone, what will think happen? The piston will immediately go up and strike the stops, right? The gas will expand. So this is a very fast process. Whenever the process is happening very fast, it is called a non-quasi-static process. And this kind of systems are very, very difficult to analyze because the properties inside the system will not remain constant throughout. The temperature and the pressure will be different in different parts of the system. So it becomes very difficult to analyze them, right? On the other hand, you see, this is quasi-static process. Okay, it is not very, very physical. Sorry, very, very practical, right? But this is something which we consider. We consider all the processes to be quasi-static process and how it is happening. How, as we said, this very, very slow, infinitely slow, right? How you can achieve a quasi-static process. Now you have the sand. Now you just keep on picking up the sand one by one. I know it is going to take infinite kind of time, but if you just simply pick the sand one by one, and eventually when you finish off the sand, right, the piston will come up here, isn't it? The piston will come up here, but it will take a huge amount of time, and you have done the process from moving from point 1 to point 2, state 1 to state 2 in infinite amount of time, and that can be considered to be a quasi-static process. And why quasi-static process is important? Because, right, they are they are basically easier to analyze, right? Because the properties remains uniform throughout, and we obtain maximum amount of work output in a power generating device. All the turbines and all everything, all the power generating device will give the maximum output if you're following quasi-static process. And if we are considering analyzing, say, power consuming device, for example, compressors, right, pumps, it consumes a minimum amount of work, right? So it becomes a standard benchmark for us to compare our actual real systems, right? Are we able to achieve that kind of efficiency or not, right? Now we are going to understand a very, very important property which is known as enthalpy. The enthalpy is a combination property, right? Combination property means it is sum of internal energy and the product of pressure and volume. So it is combination of two different things. That's why it is known as combination property. Enthalpy is very, very important if we want to study open system. Now let us try to understand enthalpy in detail. Now suppose I have an open system. This is an open system. Now what do I mean by open system? Open system means that mass can flow, go into the system, right? And the mass can come out of the system. Mass can go in and mass can go out of the system. So this is an open system. Okay? Now let me define the boundary of the system. Let me say this is the boundary of the system. So I define the boundary of the system. So this becomes my open system. Open system are also known as control volume. So I can also say this is control volume. Right? This is our control volume. Right? In short, we can also represent it as CV. Now, what is happening is that mass is going into the control volume, right? And when some amount of mass is going inside the control volume, as per mass conservation, if mass goes in, some amount of mass has also to come out, and definitely same amount of mass is also coming out. Now, let me consider a small unit of mass, right? Let me small element of mass, right? It might be liquid, it might be gas, whatever it is, right? So let me consider a small element of mass. Right? Now this element of mass, what it has at now is the internal energy U. It has the internal energy U. Now it is about to get into the system, get into the control volume. Now try to understand that the control volume is already full. It already contains mass. It is not that it is empty, isn't it? It is already full. It already contains mass. So how is that this element, let me say the area of the cross-sectional area of the element is A and this length of the element is L. Now this element whose volume is A into L, why is it going inside? How is it going inside? Who is making it go inside? Because if it wants to get inside, it will have to push some amount of mass out. Right? So where did it get all this energy from? The answer is it is going inside because the fluid, right, which is behind this element is applying some force, is applying some pressure on it, right? It will have some pressure, right? Pressure multiplied by area is the force. So it is fluid which is behind this element is applying some force on this tiny element. Now let us try to understand what is this force applied, right? And what is the work done, right? Now for that, let us assume that the fluid, this is the element of mass which is about to get inside the control volume, right? This is the element of mass which is about to get inside the control volume. And the fluid which is behind it, let us assume it to be this piston, which is pushing this piston with a force F, which is pushing this piston with a force F. Right? Now, when the fluid particle get inside, right? When the fluid particle gets inside, right? Some amount of work has been done by this piston, which is basically the fluid behind this element, right? I'm considering it to be an imaginary piston. Some amount of work has been done. So what is the work done? So the work done can be represented as force into displacement, right? And displacement is how much? Displacement is L out here. Force into displacement L, right? Work done on the element, right? So force, I can write it as pressure into area. Cross-sectional area is A. So this becomes PAL. Now, if you see A into L, it is nothing else but volume. So it becomes pressure into volume. So the work done on the fluid by the fluid which is behind it is equal to P into V. So what happens when this fluid gets inside the control volume, along with the internal energy U, it also carries, because this amount of work has been done in it, right? So this energy is being transferred to it. So it also carries PV amount of extra energy. So the total energy of the fluid which is getting inside the control volume is not just the internal energy U, but it is internal energy plus P into V. You have to understand that when we do some work on a system, right, the energy is getting transferred into the system. Now, when the scientists, engineers, they were analyzing open systems, this term U plus PV was repeatedly occurring in their calculations. So they said, instead of treating these two as different things, let us combine them into one property. And then the combination property of enthalpy came into being. So the scientists, they combined both internal energy and PV part, and they came up with a new property, which is combination of both U and PV, right, which is known as enthalpy. So you understand, you must have understood that enthalpy will be related whenever we will be dealing with enthalpy whenever we have open systems. And what are some of the open systems? Open systems, for example, we have aircraft engines, right, the boilers, turbines, compressors, water heaters. Wherever there is mass flow into the system and mass flow out of the system, we'll have to deal with enthalpy. Now, this brings us to the last topic of today's lecture. It is almost 60 minutes. The last topic is zeroth law of thermodynamics. Now, what does this zeroth law of thermodynamics say? It is a very, very simple law. It says that if two systems A and C are in thermal equilibrium, and C is in thermal equilibrium with B, A and C are in thermal equilibrium, and C and B are in thermal equilibrium, then we can say that A and B will also be in thermal equilibrium. Now, it seems to be very simple kind of thing, but back in 1930s, when it was first being proposed, right, formally, right, it was a big thing because before that, right? Why this law is important? Because this law became the basis for temperature measurement and thermometers. How? For example, let me say I have fever and I want to measure what is my body temperature. So I will take a, let me say I take a mercury thermometer. Or have you seen the mercury thermometer, everyone? So the mercury thermometer, it contains mercury inside it, right? It contains mercury inside it. So I can take the mercury thermometer in my mouth, right? In my mouth, and as a result, what happens? The mercury expands, right? The mercury expands, and we'll have temperature marking here, and we can see what is the temperature, right, of my body. Now try to understand this. When I take the mercury thermometer in my mouth, what happens is, because of the zeroth law, I can say that the glass, which is the mercury thermometer made up of, right, comes in thermal equilibrium with me, right? The body, my body temperature. Then the glass comes with thermal equilibrium with what? The mercury. And by zeroth law of thermodynamics, I can say that the mercury, it means if I am in thermal equilibrium with the glass, glass is in thermal equilibrium with the mercury, I can say the mercury must be in thermal equilibrium with me. If mercury and I are in thermal equilibrium, it means that my temperature will be equal to the temperature of mercury. So whatever the temperature mercury is showing, the expansion is happening, right? That accurately tells the temperature, my body temperature. So you see, the zeroth law of thermodynamics, it became the basis of temperature measurement and thermometers, and that is why it is very important. Now, although when I was in college, when I first read zeroth law of thermodynamics, I thought zeroth was the name of a scientist. But later on, I came to know that no, it is not so. Zeroth law was proposed much after the first and second law of thermodynamics. But this law was so very fundamental that instead of placing it at after first and second law, the scientists, they decided to place it before the first law. So what comes before first? Right? It is zeroth. Right? So basically, it is zeroth law. Right? Right? So please keep it in mind. Now, let us have a quick look at the temperature scales that we are going to use in thermodynamics. I'm not going to discuss too much on this topic. There are two temperature scales that we will be dealing with in thermodynamics. One is a Celsius scale and one is a Kelvin scale. The Kelvin scale is also known as the absolute scale. Right? So whenever we are writing down the thermodynamic equations, right, it is in the Kelvin scale. And the relationship between the Kelvin scale and temperature centigrade scale, Celsius scale, is Kelvin is equal to Celsius plus 273.15. So with this, I will like to stop the second lecture. I hope it was of help to you. Please let me know in the comments the things that you liked about this class and what are the things that you will like to improve so that I can be of better help to you. Thank you.